Again, welcome everybody. Thank you for attending this presentation. My name is Lucila Almeida. I'm part of the Rocky-Fluent team. Today, learning section is about fluidization. So, in respect to everyone's time, let's start. Well, fluidized bed is a physical phenomenon that occurs when particles, usually in a holding vessel, behave like a fluid. The usual way to achieve a fluidized bed is to pump fluid, it can be air or a liquid, into particles. The resulting phenomenon is called fluidization. And this resulting fluidization medium has many advantages, amongst which you can see the high fluid solid surface area and the intense mixing that is reached inside this device. And these two together promote uniform temperature gradients as well as enhanced mass transfer and reaction rates. The frequent particle-particle collision, as you can see here in this video, is also important for certain processes that require particle to get in contact. For example, when you want to transfer a certain liquid film from particle to the other. The fluidized bed also allow continuous state operation, and they require low investment and maintenance due to its simplicity. And exactly because of these advantages, fluidized beds are widely used in technology process, as you can see here in the list. I'm not going through this list. You can see that it's from chemical reactors to coating, several processes that require high rates for reaction max and energy transfer rely on fluidized beds. Therefore, understanding the flow characteristics and particle-fluid interaction at the particle level is key for designing and operating such fluidized bed units. And exactly that's the goal today, to show how to use the coupling between DEM and CFD methods as an interesting approach to model this equipment and get more insight on what's happening inside the devices. And here is the agenda for today. The goal here is to set up a problem. So we are going to see the problem description and see how to set up this problem using Rock and Fluent coupling. I'm not going through all the steps for setting up the problem. I'm going to focus on key points of this setup. Later on, we'll see how to perform some fluid-related analysis, focusing on the fluid particle post-processing, something that is new in Rocky. And later on, we'll finish by seeing some interesting particle-related analysis that we can do when checking the results of this fluidized bed. So for today's webinar, I chose a very simple rectangular bubbling fluidized bed, as you can see here. It has a rectangular inlet. It uses Gildard-D particles, so they are small but not so small. They have roughly 3 millimeter size. We are using spheres, as you can see on the right side here. And for this bench scale fluidized bed, we'll have circa 93,000 particles. Also, as you can see here in the middle, we'll use a hexahedral mesh, quite uniform mesh, and it has, the mesh size has a length equal to 3 diameter size. And that's important because one of the things behind this coupling approach is that particle size should not be a lot bigger than the mesh size. As you can see here, in order to make it simple, we are not modeling the gauge distributor, so we will assume a constant inlet velocity at the bottom. I mean, by constant, I mean especially constant at the bottom. The entire section has the same velocity, but this inlet velocity changes with time because we want to capture the minimum fluidization velocity. So the velocity will start from 0 and follow a ramp up to the maximum velocity, as you can see here in this plot. The other boundary conditions are quite simple. At the outlet, we have 0 gauge pressure, and for the walls, we assume no slip conditions. Again, I'm going to cover some key steps in this setup, but don't worry, okay? This is actually one of our workshops. So if you visit ROC support portal, customer portal, there you can download this workshop, and there you can find step-by-step how to set up Fluent and ROC projects, as well as how to achieve the same post-processing I'm going to show you today. And if you just want to check it out, how the problem works, you can also download files there. So you can find the Fluent setup, ROC setup, so you can just work on post-processing, for example. So if you want to follow this, visit the customer portal, there you can find this workshop among several others. So let's start here. Starting from the setup, as you can see here, I've imported geometries. There is an inlet there, and the geometry is actually the Fluent mesh. So as you can see here, it's a regular mesh. I've used Fluent mesh as the geometry here in this case. For the physics, the standard models are used except for the rolling resistance. I've added rolling resistance because I'm using spheres, but I know that my particles are not perfect spheres. For materials, we created a new one, the nylon. And here you can see that we set the density and Young's modulus for this particle. For the material interaction, of course, it's important to set up the friction coefficients as well as the restitution coefficients. These are used for the computation of the normal and tangential forces. For the particle bits, again, we are using spheres. They have a uniform particle size. All of them have 3 millimeters. And again, we added a rolling resistance, and we need to give a coefficient here to make it harder for the particles to roll, just to make they are not perfect spheres. For injecting these particles, we started with the volume fill method. So for this method, we just prescribe the amount of particle we want to inject. So here, as you can see, we have roughly 93,000 particles. They have all the same size. And to give the region at which we want to inject these particles, as you can see here, I'm using the walls to limit where the particle can be injected. And I'm also using this rectangular region to limit up to which point they need to be injected. For the CFD coupling, as you can see here, we select a two-way coupling. And for this, we need to bring Fluent file, as you can see here. As soon as I click open, ROC will validate to make sure that the Fluent file is consistent to the problem we are running. So for example, if I have thermal model here in Rocky, I need a thermal, a Fluent case that has thermal on. Next step for the interactions, I need for each particle group to give the drag law that is used for the drag force calculation. We have several options in Rocky. Here we will be using Eulerian dashboard that is a blend between WenU and Ergon. I will also add turbulent dispersion here, although this will not make much difference here, but that's an option to add a random fluctuation velocity to particles. In this case, I have only one domain. So this domain will be included in this coupling, but if in case I had several domains, for example, to make the mesh easier, I could choose. And here in Fluent, I select how I'm gonna run this problem in Fluent. So I will run in 0 because it's a coarse mesh. And this is important, I mean, only keeping the two last Fluent files. I'm not using data initialization, but in case I wanted, I could bring my initial Fluent file here. And that's it. Then I need to decide how long I should run and the frequency at which I'm going to output my result file. Finally, decide how I'm going to run this problem on the DM for the DM solver. And here I'm running using a GPU card. And last but not least, here I'm going to add an additional module that is called CFD coupling particle statistics, because this way I can get information about fluid forces acting on particles. So I can, for example, select to record drag force information or pressure gradient force information and so on. So starting the simulation, Rocky generating particles. And here you can see there is a brief summary. You can check the number of particles and time step to make sure everything is okay. This is a two-way coupled simulation, so Rocky and Fluent run side by side. So here you can see that Fluent is open. The setup is prepared, and you can see that the results are being computed as it is for any CFD simulation. And here you can see how the particles start, because we have used that volume fill process. So you can see it's completely filled, almost no space between particles. And the simulation is running again. You can see that summary here. Click and solver. And you can see any points you are monitoring, and also that convergence is okay for this problem. And we didn't have time covering details, but my goal was to show some key important points at this setup. Now let's talk about post-processing. As I told you before, release 22 R1 has some interesting post-processing tools that allows you to see what's happening to the fluid phase, not only to the particles. And let's see some of them. So here you can see that the simulation, it has run, and you can see that up to the minimum fluidization velocity, nothing happens. Then when we reach the minimum fluidization velocity, you can see the bubbling behavior of this fluidized bed. Remember that we have turned on the CFD coupling particle statistics. Again, that allows us to have information about fluid forces acting on each particle. And we can, for example, color particles for by the drag force. So here you can see at each output time, you can see what's being computed for that fluid force for each particle. But let's say you want to see what's happening to the fluid phase. You can come to the CFD coupling. Here I'm just creating a thin cube to work as a plane at the center section of this fluidized bed, as you can see here. And for this cube, I can color my nodes based on fluid property. For example, here, I can come here and color by solid volume fraction. So let me turn off particles. And you can see that I'm showing here for each fluid cell, what is the volume fraction that is actually transferred to fluid. This is used for computing velocity and pressure. So you can see here, you can see volume fraction and others such as fluid velocity. So you can see at every time what is the fluid velocity for that CFD cell. And not only you can see scalars, but you can also show vectors. So for example, if I come here, vectors, I can show the fluid velocity vectors I can make them, normalize them, and change the scale. So as you can see here, you can get a lot more insight to what's happening to the fluid phase by post-processing the fluid phase and the particle phase together. So I can turn down particle here, and then you can have a lot more insight to what's happening inside your device. Let me just show particles behind the center plane. So here you can see that we can have a lot more information on what's happening to the particles using this fluid post-processing. And of course, you can record videos using these vectors and scalars as well. When I told you that we have the option to post-process the fluid phase here, I'm not talking only about 3D views and vectors. We can actually perform quantitative analysis in Rocky. One of the things that we always need to do is to get the pressure drop in a fluidized bed, and I'm going to show you how to do this. So again, this time I will create a new cube to show the pressure. Again, pressure is one of the scalars that is available. I can create a smaller cube because I want to see the pressure at the bottom of this fluidized bed. So I'm restricting the domain into that thin cube at the bottom. And now as pressure is available, I can come to this thin cube and plot a time plot of the average pressure at this bottom. So you can see here that the pressure changed with time. Normally, that's not how we plot this. In general, we show this as a logarithmic scale. So let's do this. Just by clicking here, we have the traditional plot of the pressure drop in a fluidized bed. And here you can see that we can capture the minimum fluidization velocity where this behavior changes, and that match the experimental data in this case. So you can see you have the plot we generally want, and you can export this curve or export the image and use it in your report. And just to finish this 15-minute webinar, I'm going to show you a nice post-processing tool that I often use when post-processing coupling, Rocky-Fluent coupled simulation. So we are going to talk about Eulerian statistics. And the goal here is, I showed you that you can see the information per particle, but quite often that's not what you want. You want to see the information at a certain region according to the particles inside that region. And that's what the Eulerian statistics give you. So again, same fluidized bed results, showing information per particle. This time, let's convert this to an Eulerian vision, let's call it. Moving from discrete to Eulerian. I will create a cube here again. Let's make it a little bit bigger to encompass particles. And for this cube, I can right-click and create a process called Eulerian statistics. This Eulerian statistics will subdivide this cube into a certain number of regions, and you can change this, of course. So in this case, let's change to 3 divisions. So you can see that we have divided this domain into several subdomains. And here we can see, for example, the volume fraction for that region according to the particles that are inside that region. Let me turn off the particles. And you can see that this changes with time according to what happens to the bed. I can show, for example, the vertical velocity. So this is the average vertical velocity for the particles inside that cube. And of course, I can post-process it to get quantitative data. So that, for example, I can create an inspector and show how the average velocity of the particle change in that location with time. So you can see as I change the time, the particles that are inside that region change, and therefore the average velocity change. We have some standard quantities for the Eulerian, but we can also create new properties. So let's say I don't care about velocity, I want to check the average drag force for each location there. And there you can see I can create the quantity I want. And here you can see what is the drag force for each location there. And just like I did for the previous property, I can create a new time plot showing how the drag force change with time at that location. So for example, let's say you have a camera filming that region, you can get the same information in Rocky with the transient velocity at that region. But let's say you also want to get a time average value. So you can select the time range and also the property and get the time average value for that property. So now let me turn off inspector. I can get back to the Eulerian statistics we've created and show now this time average of the vertical velocity. So you can see it does not change because that's the time average. And here you can see the standard profile for a bubbly fluidized bed in which the particles rise up by the center and then get back to the bottom following the walls. So you can see this dual recirculation pattern that is expected for this kind of equipment. And you can do this, you can get this using this Eulerian statistics tool. I know it's a very short presentation, but I hope it's useful for you to get some insight of what can be done using Rocky-Fluent coupling for fluidized bed. And again, this is a webinar, this is a workshop. And we have detailed steps by step how to perform this analysis and also how to set up this problem using Rocky. So if you wanna, visit our portal and get this workshop. And finally, this is one of the sections. Please stay tuned, visit our website to check the upcoming section. They are quite interesting. And if you missed one of the last ones we did, you can go to our website and watch the recording in there. That's what I had for today. Thank you for attending. If you have questions, please drop in the chat.